Welcome to the second session of the day. We will have Matthias Kramm talking to us about Python typology. Let's welcome him.
All right. The quick brown fox jumps over the lazy dog. Can everybody hear me? All right. That was a sentence from typesetting. Has the property that it contains every letter of the alphabet at least once. This talk is not about typesetting. It is, however, about types. So this is an example that I claim that doesn't appear on this projector. There we go. Wonderful. This is an example that I claim could benefit from static type checking. It's a very simple function. It tries to make an announcement by sending out a bunch of emails to a group of users. And we also have a caller of that function that calls this function with a string, even though this function assumes that it's called with a list of strings. And thus, what happens is we send out a lot of emails to single-letter email addresses. So we actually had this happen at Google. And what happened was that some of these emails actually did reach their destinations. Apparently, we did have users that claimed a single-letter Unix name as their user alias. And they probably felt pretty smart about it, too, until they realized just how many emails they would be getting at every single day. So how do we fix this problem? Behold the type annotation. This is a new feature. It was introduced in Python 3.5. And it says that the only type that I'm allowed to pass as parameter in a call to the make announcement function is a list of strings. And everything else is considered invalid. And while we're at it, we might just as well also annotate the return type. So here we say that this function only accepts a list of strings, and it doesn't return anything. It returns none. This is Python 3. Strings are Unicode. Email addresses can be Unicode. They can also be byte strings or ASCII strings. So let's allow for that possibility as well. So we introduce a union type. So this now says that the make announcement function takes a list of either byte strings or Unicode strings, and it still returns none. OK, one final refinement. This takes a list of strings. It's probably also OK to pass a tuple of email addresses or a set of email addresses. So instead of limiting ourselves to list, let's expand that to iterable, which catches all these other cases. So here I've been putting type annotations directly into my program, which is nice when you can do it. And sometimes you can't, because the original author of the code doesn't let you modify his code, or you're writing code that's supposed to work on Python 2 as well as Python 3, or you're annotating a C extension where you don't have Python source code. For that case, Python now has the concept of header files, PYI files, where they have the structure of the Python program, but they don't contain any of the actual implementation. And you can stick all your types into that alongside file, and you don't have to modify your original Python source. And we've been using this to annotate the entire Python standard library with static types in a project called TypeShed. So this is the sys built-in module extracted from TypeShed. And as you can see, PYI files are like standard Python 3 files, except everywhere where there would be a method body, you just write ... So this is how you put, type annotations into your program, or if you have to, alongside as a plan B. The next question is, how does Python actually behave differently? So if we have type annotations in our programs, does it actually do anything different? And the answer is no. So here I took one of the make announcement variants I had earlier, and I just typed that into the Python command line shell. And I called it with a string, which is exactly the case we wanted to exclude before. And Python doesn't care. Python is like, yeah, that's good, keep going. And so you do need external tools to make heads and tails out of these type annotations. For Python, they're just pure comments. They get evaluated, they get stuck somewhere, but that's it. Everything else you need to leave open to external tools. There's a couple of options here. MyPy is pretty much the canonical standard. It's the tool the specification was written for instead of the other way around. PyType, which I wrote, and it's way more experimental, but it can do some things that MyPy can't. There's also PyCharm, which is not a tool, it's a full-blown IDE, but it also has support for type annotations. And the Pyland authors assure me that they're also working on support for this. So let's take a look at an even simpler example. So this is a very simple program that has a type error. It's a function that wants an integer, and I'm calling it with a string. As I said before, Python can just run this without any errors. But if I point MyPy at it, then MyPy will tell you, I found a type error in line 3. You were trying to pass a string to a function that only takes an integer. And if I point pytype at this file, then I get the same thing. And the error messages here are phrased slightly differently. But other than that, these two tools so far agree that there is a type error here and where the type error is. And that's going to be true for the next couple of slides, and then I'm going to have some example cases where they diverge a little bit. And in PyCharm, you get this yellow background on the line that has the error, and then you hover over it, and you also get the error. And PyCharm also still works for this simple example. Going from simple examples to slightly more complicated examples. So here I have a function that wants an iterable, and I call it with a list. So far, so good. That's still fine. However, I call it with a list over strings, whereas the function says I want an iterable over floats. So here too, our tools report a type error and tell us that it found an error in our program. And here the function definition itself is wrong. So this function claims I always return an integer. What it really then proceeds in doing is returning a string. So it doesn't follow its own specification. And that too is detected by type checkers. And that's detected statically. Before you even run your program, type checkers point out these problems in your program. And now this is the first example where the different type checkers actually have different ideas at what correct programs are. So this example is MyPy considers this an error. The error message here on the slide is from MyPy. It says that, well, you have this parameter that's supposed to be a string, and then you use x, parameter x, to store an integer later on, and that's an error. Whereas PyType argues, well, as long as everybody calls this function correctly, as long as everybody is calling that function with a string, that's fine. Afterwards, that function can do whatever it wants with that x parameter. So that's a general difference in philosophies between these two tools. PyType tries very hard to work on Python code that was written without type annotations and type checking in mind, whereas MyPy evolved from its own programming language that was strictly typed, so it's sometimes a little bit more rigid. And here I have an example where PyType finds an error and MyType doesn't. MyPy doesn't. So I initialize an empty list, and then I also know that I have something that is an integer, and I retrieve something out of that empty list. Now, obviously, this can never work. And no matter what, even if the integer is something quirky like -1, you can never get something out of an empty list. And PyType will tell you statically that you have this bug in your program. In all fairness, MyPy complains about this program as well, but it complains about the fact that it doesn't know what M is. Like, it's a list, but it's a list of what? You can tell it that it's a list of anything, but then it still doesn't find the error on line 3. So those were some examples for the typical kinds of problems and bugs in your code that type checkers can find for you, and also a little bit of guidance how to pick a type checker for your project. Now I want to talk about, suppose you already have Python code. Suppose you already have legacy code. You have 100,000 lines of pre-existing Python code. How do you move that code base to a statically checked build process. And the way I see it, a good start is to just point type checkers at your code as it is. Just point it at the unannotated code with no type annotations whatsoever and see what kind of bugs that reports. And you're going to get some useful results out of that. So a typical error is, well, I just import a built-in module, and I access a method in it that doesn't exist. This doesn't have a foobar method. So as I've shown you before, we do have a PYI file for this. So we have in a project called TypeShed the complete PYIs for the entire Python standard library. So a type checker can just go and look up the sys module and find out what methods it contains, and then it doesn't have a foobar method. So even though this program doesn't have any type annotations by itself, you're still using type annotations to check when you run a type checker on it. And the same is true here. So in Python, it's never valid to add an integer to a string. That's just not something that's allowed. We do have a PYI for the entire Python built-ins. The Python built-ins have a method that is called every time you add something to a string. And that method does not accept integers. So here again, even though I have a program without type annotations, I get some useful results out of running a type checker. And the same is true if you call some more obscure function deep in the standard library, and you're missing a parameter, then a type checker will tell you that that is wrong. And I like this example because you can kind of imagine this warning message being deep in some error handling code that's probably not executed well by tests. So a type checker will give you that additional add-on to tests in terms of finding bugs in your program. And finally, it also finds if you call something with the wrong type. So here, obviously math has a square root function. And the square root function takes one parameter. And mathematically speaking, it's also correct to compute the square root of a complex number. However, in Python, you need the cmath module in order to do that. The math module only works on real numbers. And here, too, a type checker can tell you, yeah, you're calling the wrong built-in with the wrong type. So that was about what a type checker can do for your code base, even though you haven't actually introduced any type annotations yet. But of course, in the long run, you do want to introduce type annotations. You want to check your method calls across your code base and make sure that your own types are sound and used in the right way and the right calls. And in that migration, our tools can help you as well. So pytype contains a complete type inferencer, which is different from a type checker. It's able to take a look at vanilla Python code and figure out what the types might be. And then you can use a second tool called merge_pyi to bring those results back into your sources. Right now, it's a two-step process. So you call pytype first, and you generate a PYI file. We've seen some examples of PYI files. It's just all the types of a given module condensed. And then you run a second tool that's called merge_pyi, and that transports that back into your actual source code. And we might merge those two into a common tool at some point. But due to the fact that it's a two-step process right now, it makes it easier for other people to write their own experimental type inferencers. For example, there's a tool called make_step files that does the same thing. You point it at a file, and it generates a PYI file with all the types, and then again, you can run merge_pyi, and you get that back into your sources. So some examples of how type inference works and what it can do. So here we have a very simple function. It's called getLabel. It returns some capitalized name that we have stored. Now, for the sake of argument, let's assume that we don't actually know what the name attribute is. We don't know the type of that. We only see the function in isolation as it is here. Now, so all we know for the return type of this function is that it's something returned by some capitalize function in the built-ins or other types. And type inferencers will assume that, well, there's an obvious choice of the string type. The string type is capitalized. It returns a string again. So we assume, we infer that this function returns a string. And the same is true when you infer the type of an argument. So here we have the D parameter. And whatever D is, we know it has a keys method. And that keys method returns something we can iterate over. And the elements of that sequence all have a starts with method. And from that, pytype will derive that this is a function that takes a dictionary that maps strings to something and also returns a dictionary that maps strings to something. And you'll get that annotation out of the box. So just pytype and merge pyi, and it will annotate functions like this without you having to do anything. Sometimes what you get as the result of type inference depends on what kind of modules you include. So here I have a function that has one parameter, f, and we call read on that one parameter. Now there's only one built-in type that has a read method, and that's file. So normally we would assume that read byte takes a file parameter. However, this module also imports string IO. And string IO also has a type that has a read method. So we can derive that this function takes either a file or a string IO to string IO. And I have two more examples for this. This is a fun little function. It takes one parameter, I, and then it looks up the index in an array at that position, I. So in effect, for 0, 1, and 2, it will add 1 to the number you pass in. And if you pass -1 or a negative, then it will subtract that from 4. So we would assume that this is a function that takes an integer and returns an integer. Except we forgot about the built-in Python slice type, which is a type that's totally legal to instantiate on its own. And if you pass that to this function, then you get a list of integers back. So the real method signature is actually more complicated in this case. And that's pretty typical for when you do automatic annotation of your program. You always find that your code is way more generic than you thought it would be. And your functions accept way more types than you thought it would. Here's another example for that. So I have a function that converts miles to kilometers. Obviously, this returns a float. The parameter m can probably also be a float. It can also be an integer, obviously. But what we forgot about is complex. Of course, I can pass a complex to this function, and then it will actually convert two distances at once. It will convert the distance in the real part and the distance in the imaginary part. And for all you know, somebody in your code base is using that exact feature of your miles to kilometers function to convert distances twice as fast. So in that case, it would be useful to drop out the additional types that you don't actually want people to pass and run the static analyzer on your entire code base again and just see what kind of calls now break to figure out who was using your function incorrectly. And that's something that wasn't possible in Python before, out of the box. So I want to talk about a few more things that we plan in future versions of PyType. One thing is duck typing. So earlier you saw me giving these long lists of types. I have a union type of int, or a float, or a complex, and so on and so forth. And that's not always the best way to actually express a type. Sometimes it would be more convenient to describe a type by what you actually want to do with it. Here I have a function that all it really does with its one parameter is it calls float on it, so it converts it to a float. And in order to annotate that, I just say supports float. So I just need the parameter pressure to be able to support float. And suppose we have some other class that we want to use as an argument to this method. And this thing doesn't register itself with any abstract base classes. It doesn't inherit from anything. But the idea is that as long as I implement a float class on this method, as long as I make this class compatible with the protocol I've laid out, then it should be OK to call this other function with it. The additional further feature we are working on is, so earlier you've seen me, point pytype at individual files in isolation, and I got errors out of that. What if you have more than one file? Like, what if you have multiple files in your code base and they end up using each other, which code bases tend to do? What currently happens is if you point pytype at the first file, it will tell you, well, I don't know anything about this B thing. Can you give me a PYI to describe that further? So I've shown you that pytype, you can point it at a Python file. It gives you a PYI file, so it extracts all the types for you. So you could point it at b.py, and then you could analyze a.py. Suppose we have a more complicated import tree. We have a.py, and a.py imports b.py, and c.py, and d.py. b.py imports e.py and f.py, and c.py also imports f.py. So in order to analyze this, we generate the PYI for f.py, we generate the PYI for e.py, then we can do the next layer. b.py, c.py, d.py need to be generated, and finally we get to analyze a.py. Analyze a.py. So that's really cumbersome on a large code base. So we're working on a tool that simplifies that and either generates makefiles for you or just runs Python for you, something along those lines. So it would look at your entire source code, pull out all the imports, build the import graph, put everything into the right order, and then analyze your entire code base. And in working on this tool, we generated a few import graphs of popular projects. So this is Mercurial. And Mercurial is a pretty nice code base, actually. So this is very much DAG-like. So all the entry points are at the top, and they call things further down. And that stuff calls things further down until at the bottom, everything only depends on this Python standard library or extension modules. And the Python standard library is similar. It's all the high-level modules are at the top, and then that calls things in the layers further down. The little head-looking things here, those are init files that pull in everything in a subdirectory. And then at the bottom, everything only depends on extension modules and so on. So these were two relatively well-behaved code bases. This is Network X. Network X, ironically, is a tool that you can use to analyze the import graphs I'm showing you here. It has this one central init file. And that one central init file imports everything in the entire code base. And then everything in the entire code base uses the central init file. So it's like this giant super circle of circular dependencies. So I was happy when I found that. And finally, we have the Google code base. There's unfortunately very little I can tell you about this. What I can tell you is that the isolated, convoluted green thing at the upper left, that's the YouTube code base. All right. That's all I got. Thank you so much for listening.
Thank you, Matthias. At this point, we will open the panel for questions. We have around 5 to 6 minutes for questions. So feel free to make a line here for the mic.
Hi. The duck typing thing that you're working on, will that support only official protocol type duck typing with under methods, or could you define your own interfaces sort of in the style of Go and have classes implicitly implement them?
The idea is to actually be able to implement, define interfaces. So you would have something that looks a little bit like an abstract base class. You'd have a class decorator on top of that to mark it as an interface. And then everything that implements the methods in that interface would adhere to the interface.
That's awesome. Thank you.
Hi, so it's a two-part question, and I think I'm probably missing something, but your motivating example settled on an iterable of a union of string and bytes, right?
Yeah.
So I think, at least, I just tested this in MyPy, I don't have PyType installed. I think that a string is an iterable of a union of string and bytes. It's an iterable that returns single character strings. So MyPy at least doesn't actually catch that failure example.
That's good. Thank you for pointing that out.
It's not a gotcha because I'm wondering if there's a nice, I mean, obviously you could do a union of all of the iterables other than string, but then if a new iterable is added, that wouldn't catch it. And that suggests that what you need is something like a difference type. But I don't think that 484 has difference types, i.e. any iterable but string.
Yeah, difference types are tricky. They usually make your type system way more complex and also have quite an effect on programmatic, on CPU resources. Yeah, that's true. In this case, you would probably actually still just say list or actually enumerate. I want list or sets and tuples, and that's it. No iterables. Yeah.
Right. Or just an assertion, guard it, the old way of guarding it at the front. But anyway, thanks a lot.
That's a really good point. Nobody else had found that.
So the Python interpreter completely ignores type annotations, and the tools you described, as far as I can tell, they only do static analysis. So do any tools exist that can enforce type constraints at runtime?
Yes. So there are a couple of tools that do runtime enforcement of the type annotations you can put into your programs now using PEP 484 and Python 3.5. All the tools I've seen so far need a decorator. So you don't need to put anything into the decorator, thankfully, but you need to put a decorator on top of the function that says, check the type annotations of this function at runtime. In theory, it would be possible to, build an extension module that you just register with Python, and it, screws with the data structures of Python enough so that you wouldn't need that, which would be a neat thing to write. But right now, everything I've seen, you put this extra decorator in place, which is OK, because you need to touch the function anyway to introduce the type annotation, so you can also add the decorator, and then people know, hey, this is runtime type checked, and know that this is performance implications, and that you need to be really careful when you call this function, because things might blow up.
Hi. Have you done any work towards including the parameters of types like, so for instance, if you have a NumPy array or a pandas data frame, they have a shape. Do you think it would be possible to verify the shapes or infer the shapes of these containers?
So you're saying automatically figure out that it's like a 3x4 matrix?
Or n by n given some input of something by n.
Or, because
it's not in the types.
When you say n by m, do you mean like with n beyond a given bound, or that n is larger than m, or?
Well, so given, say, a matrix multiply of a matrix of n by m multiplied by m by k, and you would infer that you get a matrix of n by k.
I see. So you want to catch the case where the two dimensions don't line up.
Yes, and often these things run for a long time before you find the error, and having the type system do that might be useful.
I think that would definitely be in the realm of static checking. It's kind of outside of the scope of static type checking, because you're not really talking about types anymore. You're talking about values. You're talking about the concrete integer 8 that needs to line up with that other concrete integer 8 over there. Unless both dimensions would stem from the same variable, you can somehow infer that they both come from the same constant that is defined somewhere. Then it would still be something that you could argue belongs to type checking.
To abstract over all the other questions so far, what are your thoughts on parametric polymorphism?
Parametric polymorphism. So that was the one where you get to overload a function a couple of times?
Any kind of type variable abstraction, basically.
Type variable extraction. Yes, I mean, I've extracted some type variables, right? I mean, here we have a type variable. The union int comma, sorry, not here. Here we have a type variable. So here the dictionary actually is an, polymorphic class, and it has 2 type parameters. And I'm filling in the first type parameter using a string.
Right, and a more parametric version would have the values in the dictionary not being any, but being some unspecified type.
Yes. So the question would be, how do I make it so that I know that here in the function signature, any is replaced by the same type variable, right? Yeah. Yes, we do have the data structures for that around in PyType. And that's something we really want to do. It's not like the highest priority because, I mean, for type checking, this function is already pretty good. But yeah, that's something we want to get around to at some point.
Thank you. So hopefully quick one. On the int slice one, you're using unions on both the parameter and the return type. Have you looked at using the overload capability at all to match up the particular input types with the particular output types?
Yeah, I don't have any slides for that, but we definitely do that. So if we find out that one possibility is that this function, yeah, like the int slice example. So we do have versions of the code that just splits that into 2 functions, and you get the int version and the slice version. And that's sometimes useful to get more concrete results when you do type inference.
OK, let's thank Matthias for the talk.